Okay, good morning to everyone. Today's class I'm going to discuss about. These are the contents. In today's class we are going to discuss MOS transistor and transistor as switches. What are the types of switches? How they can perform as a switch? And NMOS transistor, PMOS transistor. So there are two types of MOS transistor here, and also CMOS logic. And also we can discuss about the basic MOS transistor actions, that is NMOS enhancement mode and NMOS depletion mode. All those things we are going to be discussed here. So firstly, this is the field effect transistor flow diagram. Here it is. These are the types of field effect transistor. Already you know that you learned from the electronic devices circuit. Okay, so this is the FET here. It is classified as two types, that is N channel junction field effect transistor, P channel junction field effect transistor, and also another part is nothing but MOSFET, metal oxide semiconductor field effect transistor. So in that metal oxide semiconductor field effect transistor, it is again classified as two types, that is enhancement mode field effect metal oxide field effect transistor, depletion mode metal oxide field effect transistor. Okay, again the enhancement mode, there are it is classified as two types, that is N channel and P channel. Similarly in depletion mode, N channel and P channel. So this is the basic flow of field effect transistor. But actually no need to discuss about this concept here, but you need to gain some information. You need to know some information whatever we have learned in previous subject. There we have discussed, that is field effect transistor. So from that we can classify these metal oxide semiconductor field effectors. So that's why I am showing here, that is field effect transistor. Okay, and here now I'm going to discuss about metal oxide semiconductor device. As you know, here the metal oxide semiconductor field effect device is nothing but it is a voltage controlled resistance device. Voltage controlled resistance. Suppose you know it is having three terminals. So let us see here: drain terminal and gate terminal and source terminal. So here you can apply the input, whatever the data you have to apply, the data will be applied at gate terminal with respect to source, that is nothing but VGS. Okay, so here by applying this voltage, the device is going to be on condition and off condition. If the device is going to be on condition, it occupies very less resistance across this particular device. If the device is going to on condition, it occupies very less resistance across this particular device. Suppose the device is in off condition, it is going to be very high resistance, that is in terms of mega ohms. Okay, when it is occupies less resistance, means the device is going to be in on condition. The resistance across the particular device, it is in terms of ohms. Okay, that is the resistance properties of this particular device. Whereas it is in on condition, it occupies very less resistance, it is in terms of ohms. Suppose the device is going to be in off condition, it occurs across the device, it is having very high resistance, it is in mega ohms. Okay, so here, that's why here it is figure, it is called as a MOS transistor as voltage control resistance. Okay, so this is the terminal 2 is the gate terminal, and this is the drain terminal, and this is the source terminal. By applying voltage at the V input, the resistance will be varying. It is going to be varying. Okay, if you applied input voltage 0, then the resistance is very high. Because suppose if it is N channel device, here we are applying the 0 voltage here, then the NMOS is going to be off condition. It occupies, or it is having the resistance is very more resistance in terms of it is mega ohms. Suppose if you are applying logic 1 here, nothing but VCC or VDD, then it is going to be on condition. it occurs very less resistance. It is ohms. That is the variations of resistance, ohms to mega ohms to ohms. That's why here it is shown. He represented with the variable resistance here. Okay. So already know that drained metal oxide semiconductor device, it is having three terminals. Okay. Let us discuss the first point here. A MOS transistor is three-terminal device. It act like as a voltage control resistance device. An input applied to one terminal that controls the resistance device, resistance of the device. Okay, an input applied to one terminal that controls the resistance between the remaining two terminals. Okay, so here the input voltage applied at the one terminal that will be controlling the resistance between the remaining two terminals. And similar way here, whatever we are applying the data at the one terminal here, due to that input voltage, the remaining two terminals are act as like at a short circuit also. Then only the device is going to be on or off condition based on the applied input voltage. Okay, you know that the metal oxide semiconductor is classified as two types, such as one is N channel, it is called as NMOS, and another one is P channel, that is called as PMOS. So these are the circuit symbols of MOS transistor here: NMOS transistor and PMOS transistor. Right here, the drain is terminal is shown like this. The NMOS structure or NMOS circuit symbol is shown like this, and the PMOS circuit is shown like this. Okay, right? Clear? Right. Next. So here, advantages of FET over conventional transistor. Okay. So here, you know that bipolar junction transistor means there the bipolar junction transistor, there only it is having two junctions that have two junctions, that is base emitter junction and base collector junction. So we are observing the current is flowing due to the both charge carriers, minority charge carriers and majority charge carriers. Whereas in metal oxide semiconductor device, here we can observe only majority charge carriers only, either electrons or holes. Okay. Next. So the advantage of field effect over conventional transistor is here it is a unipolar device, whereas BJT nothing but bipolar junction device. Bipolar device. There the current is flows through the both charge carriers, electrons and holes. And here only it is a unipolar device. Only that the current flow is or the current carries through the only major charge carriers only. That is one type of charge carriers only, either holes or electrons. Okay, that's why here it is a unipolar device. That is, the operation depends on only one type of charge carriers. Okay, that is called as holes or electrons. Next, the voltage controlled device. That is the voltage control device. The gate voltage controls the drain current. How the gate voltage will be control the drain current, I will show you in next slides. Okay, based on this gate voltage, based on this gate voltage, the channel is available, and also that based on that gate voltage also the channel will be removed. How the channel is established, how the channel will be removed, we will discuss in later, and how the drain current will be depending upon this gate voltage. Right. Next, it is very high input impedance. It is very high input impedance. The next point is source and drain are interchangeable in most low frequency applications. Next, the low voltage, low current operation is possible. Okay, and less noisy as compared to bipolar junction transistor. No minority charge carriers, storage turn off as faster, and very small in size, occupies very small space in integrated circuits. So these are the comparison of unipolar device over bipolar junction device, right? So coming to the switching model of NMOS and PMOS transistor. As you know, the metal oxide semiconductor device is classified as two types, such as one is N channel, nothing but it is NMOS, and the other one is P channel, nothing but PMOS. Generally, here we are showing N channel and P channel device only, okay, instead of NMOS and PMOS. So come to this point here. This is the N channel device. Here it is, and this is the P channel device. These are the symbols of the circuit symbol of the N channel and P channel. So let us observe the difference between these two. Both are same, but there is a slight difference here. It is bubble is occurring here, but here it is not a bubble. Okay, here the bubble is available. Here there is no bubble. So means it is there is no bubble means it is a N channel device. If the bubble is available at a gate, it is nothing but P channel device. Okay, so here this is a source terminal, this is gate terminal, and this is the drain terminal. Okay, similarly it is having source, gate, and drain. Now we want to observe the switching positions of this particular NMOS and PMOS. So let us come to this NMOS device. Here open, nothing but off. Gate is 0. Okay, if you are applied voltage at gate with respect to source, nothing but it is VGS. VGS nothing but gate voltage with respect to source. Gate voltage with respect to source, nothing but VGS is nothing but input voltage, that is V in. So based on this V input voltage, the device is going to be open circuit or closed circuit, off or on condition. Okay, so here the gate voltage is 0 is nothing but VGS. It is nothing but it is a VGS case. Okay, so then here the device is going to be off. So means it is act as a open circuit. So that voltage nothing but VGS is less than VT. VGS nothing but it is the input voltage, that is with respect to source at gate, that is less than VT. VT is nothing but threshold voltage. Threshold voltage nothing but it is a minimum level of input voltage. If your applied voltage is exceeding that level, then only the device is going to be changing its conducting property. Okay, so next, here suppose the device is going nothing but on condition. Here your applied voltage VGS is greater than VT. Okay, here VGS is greater than VT, means here the applied input voltage is greater than that exceeding level of the threshold voltage. Then only the device is going to be one position to another position. So here off position to on position. Then only the switch will be act as a closed switch. Then it will be offering the resistance here. Okay, based on this voltage, the resistance will be going to be controlling here. Okay, clear? Next case, in PMOS or in P channel device, here it is going to be off state when we are applying gate input is 1. Here we are applying gate input is 1. Okay, so here where at a P channel device, here the device is going to be off condition means it is open, and here it is on condition means it is closed, like act as a resistance. Okay, so here whereas in PMOS, here it is going to be the at gate terminal it is having a bubble. If you are applying input voltage is 1 here, so that 1 will be inverted as 0 here, that 0 will be entering into this case, then the device is going to be off. So then only the device it acts as an open switch. Suppose if your applied voltage is 0 here, so then the 0 will be converted as 1, that will be enter into this case, the device will be going to be on condition. That is the internal behavior of this particular area. Okay, so then the device is going to on condition, then it will act as a resistance device. So whereas 0 is gate applied at a gate, the P channel is going to be on, whereas 1 is applied at a gate, the P channel is going to be off state. So let us compare these two devices. So here at 0 is at gate, here 0 is at gate, here the N channel is off, here the P channel is on. Similarly at gate 1 in N channel, here at gate is 1 in P channel. So compare this. N channel is going to be on condition, P channel is going to be off condition. Let us listen carefully here. These are the basic off and on conditions of this particular devices. It is very helpful to you how to make the circuit diagram in next cases, right? So these are the metal oxide semiconductor divisor transistor symbols. Okay. So commonly we can use, these are the symbols in our circuit diagrams here. That is nothing but N channel and P channel transistor. Okay. Here the NMOS device you can use this way or this way. And next one is NMOS depletion mode. You can use in this format or in this format. And the P channel is enhancement mode. You can use in this way or in this way. So let us carefully observe here. The arrow mark is going like this here, and the arrow mark is going to be outwards. Okay, right. So here, as I told you, the N channel device is having in enhancement mode and depletion mode. The P channel is having in enhancement mode. Actually, the P channel depletion mode is available, but most cases we can use PMOS enhancement mode only. That's why he can represent here PMOS enhancement mode device only here. PMOS enhancement mode. So here there is no channel. There is no channel here. That's why he called it as a NMOS enhancement mode. Here the thick bar here, nothing but the thick bar is represent nothing but the channel is available. The channel is available. Nothing but the device is in depletion mode. But here there is no thick bar is available here. Means the device is enhancement mode. There is no channel. Okay. And one more thing here, there is no bubbles at gate terminals. Here the bubbles occur at the gate terminal. Nothing but it is a PMOS. Mostly we can use this is the we can use this type of symbols in our construction of various logics circuits, right? And now this is a basic MOS transistors. Now let us observe the basic MOS transistor structures here. Let us observe the three diagrams here. As I told you in previous classes, this is the NMOS enhancement mode transistor. This is NMOS depletion mode transistor, and this is PMOS enhancement mode transistor. Okay. Here the thick bar is represented nothing but this is the where when the thick bar is available, the device nothing but depletion mode. So let us see here. So this is the channel here. This is the channel is already available. Implant due to this implant. Okay, the implant nothing but the channel is available. Nothing but it is a depletion mode device. So here let us see here there is no channel. Here there is no channel here. So that's why it is NMOS enhancement mode transistor. Whereas in PMOS enhancement mode transistor there is no channel, nothing but it is a PMOS enhancement mode transistor. So let us observe the careful here basic differences of this difference of this structures of NMOS enhancement mode transistor and NMOS depletion mode transistor and PMOS enhancement mode transistor. Okay, so these are the key material layers here. We can construct the basic structures of NMOS enhancement mode transistor, NMOS depletion mode transistor, and PMOS enhancement mode transistor. Okay, so these are the three terminals: source terminal, gate terminal, and drain terminal. Okay, so basically here the purpose of the source is store the charge carriers, store the charge carriers, and the purpose of the drain terminal is collect the charge carriers, collecting the charge carriers from the source. How the drain terminal is collecting the charge carriers from the source? If there is a channel, the charge carriers are moving from source to drain region by the applied gate voltage. Okay, as I told you in previous slides, how the gate voltage is established the channel in between source and drain. So here it is the NMOS enhancement mode device. By applying positive voltage here, we can apply the channel in between source and drain at gate in this way, like in this way, right? Let us observe this figure here in this way. So the channel is available here. Whereas we can apply the drain voltage, that is nothing but VDS voltage. Then the charge carriers are moving from source to drain through this channel. Okay, so when the charge carriers are moving from source to drain region, the drain current is moved from drain to source region. So This is the region, the drain current carrying the current by the applied gate voltage, right? Next. In PMOS enhancement mode transistor, here we can apply the negative voltage, negative voltage here. Due to this negative voltage, we can establish the channel in P channel enhancement mode device. Okay, and here this is the P diffusion regions, and here this is the N diffusion regions. Okay, and this is positive ions here negative ions here. The P substrate, N diffusion regions at source and drain, and substrate is P diffusion region. Again, here source and drains are N diffusion region, and P is the substrate is the P type region. Okay. Next, let us see here. Let us examine the basic NMOS enhancement mode and the depletion mode transistor as shown in figure. Figure A and B are nothing but NMOS enhancement mode and depletion mode transistors, and the figure C shows the basic PMOS transistor structure of enhancement mode device. Okay, this is the basic MOS transistor devices. Okay, clear? Next, how the internally the channel, how the channel is available, how the device will be having in the internal structure. Just give a clarity based on this particular circuit diagrams. So here let us observe here. So here, as I told you here in previous slide, this is N plus region, and this is nothing but P region. N P, P N, nothing but PN junction there. Okay, like this. Like way it is, he is given as one structure here. This is a negative terminal, and this is the positive terminal. This is nothing but PN junction there, right? Okay, next, and here it is one of the this is the transistors here, gate terminal, source terminal, drain terminal. Gate is vertical here, and the source is here, and drain is here. Again, here N plus region. This is a P substrate. Majority charge carriers are positive ions, so nothing but it is positive terminal. Here the negative N plus, nothing but here the diffuse region N plus, nothing but electrons are majority here. Those are negatively charged ions, nothing but negative terminal here, positive terminal here. These two areas will be attached one PN junction there, like that. Okay, and here by applying this gate voltage, the channel is established in between source to drain. Okay, so coming to this P-type device here, the substrate is N-type. Okay, the substrate is N-type here. So here the diffusion is P plus. Okay, see here, this is the diffusion is P plus. Here the P plus. The substrate is N-type here. Okay. But in case of N channel, the substrate is P type. In case of in P channel, the substrate is N type. It's a complete opposite to the basic structure of this particular MOS transistor. Okay, let us see here. N plus diffusion. Here it is a P plus diffusion region. Majority charge carriers are nothing but holes. Those are positive charge ions. And here this is a N substrate. It is having negatively charged carriers are more. So it is negative charge area. So that's why it is represented as a negative terminal. This is positive terminal. So now it is like as a PN junction there. Similarly, negative ions, positive ions here, it is also having like a PN junction there. So nothing but here the gate junction will be act as a PN junction there. So here it is a source terminal, this is a drain terminal, this is a gate terminal. Here there is a bubble, nothing but it is a P channel device. So let us observe this point here. In the NMOS device are formed in a P-type substrate of moderate doping levels. Moderate doping level. The source and drain regions are formed by diffusing N-type impurities. In this case, N-type impurities through suitable masking into these areas to give the desired impurity concentration, and gives rise to depletion region, which extend mainly in the more lightly doped P regions. Okay, how this process is exposed to form the N-type transistor and P-type transistor, I will give the detailed clarification in next class. But this is the basic information is going to be behind this formation of particular NMOS transistor and PMOS transistor. Similarly, the PMOS transistor structure for enhancement mode is device this one. Okay, so the source and drains are isolated from one another by two diodes, right? Next, enhancement mode transistor action. Enhancement mode transistor action, right? So this is the enhancement mode transistor. How the enhancement mode transistor is going to be depletion mode, and then how it is going to be operated, how it is going to be generating the whatever we need characteristics, that is drain current with respect to gate voltage, how they are going to be performed based on some conditions. So very important, it is the very important topic here. Okay, firstly, he is given as VGS is greater than VT. As I told you, when the VGS is less than VT, if the VGS is less than VT, then the device is in enhancement mode device. But here he is given as VGS is greater than VT. In this case, the device is enhancement mode device, means there is no channel in between source to drain at gate terminal, at gate junction. But whereas here he is given as one condition, that is VGS is greater than VT, means already the channel is, due to this voltage, due to this condition, the channel is established in between source to drain. Okay, like this. This is the channel, right? So here we are applying the input voltage at gate with respect to source. So due to this VGS is greater than VT, then only the channel is established in between source and drain. So, and then after this condition, the device comes from enhanced mode into depletion mode. That's why he says enhancement mode transistor action. Okay. Second case. But here, one more point is here, that is VDS is 0 volts. VDS is 0 volts, but VGS is greater than VT. The channel is available, but there is no charge carriers are moving from source to drain. Because of here the drain voltage is 0 volts. Okay, so due to that 0 volts applied at a drain, there is no movement of charge carriers from source to drain. So there is no movement of charge carriers, means obviously there is no current. And second case, VGS is greater than VT, means the channel is available. Now we can apply a slight amount of voltage at a drain. That is VDS is less than VGS minus VT. The applied voltage is slight greater than this VGS minus VT. Now the device is non-saturated mode. Non-saturated mode means it is in active region. Simply we say it is an active region. So by applying some amount of voltage at drain, the maximum number of charge carriers are moving from source to drain. Then only we are expecting the current is generated. That current nothing but IDS, drain to source current with respect to applied VGS and VDS. Okay. So by applying this VDS voltage, the current is going to be source to drain. But let us see here. This is the condition here. Now the device is going to be non-saturated, right? In third case, VGS is greater than VT, means the channel is available, and VDS is greater than VGS minus VT. Whereas in this case, VDS is less than VGS minus VT. But in this case, VDS is greater than VGS minus VT, means maximum number of charge carriers are moved from source to drain. So due to this maximum amount of voltage applied at gate, there is a charge inversion is occur across the channel. Due to that IR drop across the channel, that will be affect the channel length will be reduced. The channel length will be, and width is also reduced due to the maximum voltage drop across this source, and here it is charge inversion will be occurs across the drain region. So due to this effect, the device is saturated. Okay, the device is in saturation condition, whereas VDS is greater than VGS minus VT. The current will be going to be like this. Suppose here it is VDS, here it is going to be IDS. So slowly the current will be increases by applying the input voltage VDS. So when at maximum VDS, nothing but VGS greater than VGS minus VT, the current will be suddenly increases. Okay, so that is the way here happening in this case. So constant means there is no current here. This is constant, nothing but it is this region nothing but pinch off region. So means there is no current in between source to drain because of the channel is disconnected in between source to drain due to this amount of voltage. So this region is nothing but call it as a pinch off region, right? So this is the basic action of enhancement mode transistor action. It is the one of the important topic, right? So coming to the in detail view here, in the first case here it is to gain some understanding of this mechanism. Let us further consider the enhancement mode device from the figures. Okay, to understand three sets of conditions here, it must first be recognized that in order to establish the channel in the first place, a minimum voltage of threshold level Vt must be established between gate and source. That the case one is case A, VGS is greater than Vt and VDS equals 0. So due to this case, the channel is established in between source and drain, but there is no movement of charge carriers. Similarly, in second case, VGS is greater than Vt, but VDS is less than VGS minus Vt. There is a slight amount of voltage applied at drain instead of this case. Then the minimum amount of charge carriers are moved from source to drain. Similarly, in third case, here VGS is greater than Vt and VDS is also greater than VGS minus Vt. The maximum number of charge carriers are moved from source to drain. The maximum voltage drop is occurs across the source region near the source. That will be affecting the maximum amount of voltage drop occurs across the channel. There is a charge inversion will be occurs at the drain. Means due to that effect, the channel will be disconnected between source to drain region. So then one region is formed there, nothing but it is a pinch off region, and the current will be constant, right? So note here, one note is given here. VDS is the drain to source voltage. Substrate assumed connected to be 0 volts. Substrate nothing but here this is the substrate here. Substrate nothing but 0 volts, right? Next point. Since the channel resistance between drain and source, and if drain is bias higher than the source, then the potential between gate and channel will be decreasing from source to drain region. So due to this effect, the pinch off region will be occurred across the channel between source and drain region, right? And next one, depletion mode transistor action. Simply, he says something about here. A depletion mode means the channel is already in a depletion mode device, even VGS equal to 0. But we know that there is a slight amount of voltage applied at a gate that will be greater than the threshold voltage. Then only the device is going into convert into enhanced mode into depletion mode. But he says here already the device is in depletion mode, even VGS equal to 0, right? Even VGS equal to 0, the device is already in depletion mode device. That will be occur at the manufacturing stage, right? Let us see the point here. For depletion mode device, the channel is established due to the implantation that will be occur in the manufacturing stage, even VGS equal to 0. And to cause the channel to case to exist, a negative voltage VTD must be applied between gate and source. Then only the device will changes from depletion mode into enhancement mode. Negative voltage is VT means threshold at a depletion device. Threshold voltage for depletion device that will be applied at gate to source voltage. Then only the device will be changing its properties from depletion mode into enhancement mode device. So here the VTD is typically less than negative 0.8 VTD depending upon the implant and the substrate bias, but the threshold voltage difference apart, the action is similar to that of the enhancement mode transistor. Okay, so whenever we can apply this amount of voltage, then the transistor will going to be act as a enhancement mode transistor from depletion mode into enhancement mode, right? So let us. So here one more concept here, nothing but actually there is no need of this concept to explain here. But you know how the CMOS logic will be formed. What are the components we are needed to be develop the CMOS logic circuit? That's why I am going to be displaying here. making this concept here again here also for the gain some information about the concept CMOS logic, right? You know that PMOS and NMOS. Simply the CMOS nothing but combination of metal oxide semiconductor devices. So what are the semiconductor devices here? We know that there are two types of semiconductor devices, such as nothing but one is N channel, another one is P channel, right? So for the combination of P channel, N channel, it is formed as a CMOS logic circuit, right? So this is the PMOS logic circuit. PMOS device here and NMOS device here. The combination of this circuit is nothing but the combination of this particular device is nothing but called as CMOS logic. So let us see here point here. The CMOS logic is a combination of PMOS and NMOS transistors. Okay, as shown in the figure. The input is labeled with the I. The input is labeled with the I, and the output is labeled with the O. So this one. Before going to verify the function of CMOS logic, let us know MOS transistors, PMOS and NMOS. I already done this concept. Okay, here the PMOS is having three terminals. This is nothing but a drain terminal. This is nothing but source terminal, and this is nothing but drain terminal. Sorry, gate terminal. Similarly, this is the NMOS device. It is this time nothing but source, and this nothing but drain terminal, and this is nothing but gate terminal. Okay, the common gates of P channel and N channel are make it as a common terminal in nothing but input terminal, and the common drain terminals of PMOS and NMOS are connected together to take it as a common terminal as output terminal, right? So this is the basic structure of a basic circuit diagram of complete circuit diagram of CMOS logic, right? So based on this concept, now we want to discuss this waveform here. Simply, you know that here, if you are applying input is 0 voltage here, 0 volts, then you know that if the 0 voltage applied at gate of P channel, how it is going to be performed. If the 0 voltage applied at gate of the N channel, how it is going to be performed. Already known that we discussed in previous slides. So based on that concept, so let us observe here the 0 voltage applied at input. So then the PMOS is going to be on. At the same time, the NMOS is going to be off condition. So means that when the PMOS is going to be on condition, there is a short circuit occurs in between VDD and V output. So here V nothing but 5 volts, here nothing, it is 5 volts like that. Okay. And there is a short circuit is available VDD to V out, that is nothing but output voltage terminal O. So now the output is nothing but 5 volts. Okay, 5 volts. And here there is no way to discharge whatever the response we are getting, that will be discharged to ground through this N channel, because of it is act as a short circuit. Open circuit. Due to this, applied 0 volts. Now we can apply the logic 1 here. Okay, at the input, then the P channel is going to be off condition, the N channel is going to be on condition. So due to that applied voltage at gate for the common terminals, the N channel is going to on and the P channel is going to off. Now the connectivity VDD to output is disconnected. Now the connection is formed. The path is formed in between output to ground. Whatever the data is available here, that will be discharged to ground through this NMOS transistor. Finally, we are getting here it is 0 volts. Okay, so let us observe here, whenever we are applying input is 0, we are getting output is logic 5 or logic 1. Suppose 2, we are applying it as a 5 volts here, nothing but logic 1, then we are getting output as 0 voltage. So you know, if you are applying input is 0, then output is 1. Simply it is act as an inverter. So here we were designed here the CMOS logic, but it is performing the inverter operation. Means here the inverter logic gate is designed by using MOS transistor. Simply we can say here it is, right? Now coming to this waveform here. So here it is 0 voltage. The x-axis we are taking the V input and the y-axis we are taking the V output. Initially it is 0 volts. Initially we are applying input is 0 voltage. So then 0 voltage means PMOS is going to be on, NMOS is going to be off. Write this. PMOS is going to be on, NMOS is going to be off. So VDD to output is connection is available. So maximum amount of voltage will be going at the output. That is VDD. V out equal to VDD, 5 volts. but practically it is like 4.7 or 4.3 like that. But theoretically we can say here it is 5 volts, that is VDD. So and again here the input voltage slowly increases from 0 to 5 volts. From 0 to 5 volts, at certain point both are going to be on condition, means partially on and partially off, or partially off or partially on. So then there is a path from VDD to VSS is formed. Okay, there is a path is available VDD to VSS. At that case we can't define the output response either 0 or either 1. So that is the both cases. The output response will slowly fall down like that. Slowly it is discrete into, it will be slowly fall down at partially on and partially off condition. Then the path is available VDD to VSS. So at that case we can identify the output response is unable to say the output response is logic 0 or logic 1. Okay, so when the V input is exceeding this level, this level, then the PMOS is going to be off condition, N channel is going to be on condition. Means greater than some voltage here, the input is going to be like a logic 5 volt, then the PMOS device is going to be off condition, NMOS device is going to be on condition. Now the connection is available in this way. Whatever the response is here, that response will discharge us to be ground. Finally, we are getting output response is 0 like this. Okay, but practically there is a slight amount of voltage, that is like 0.3 or 0.2 like that. Okay, so this is the basic concept of CMOS logic for the construction of CMOS logic by using NMOS and PMOS devices. Right? Thank you.